Okay. So in that basic types of FACTS controller, there are four types. That is series controller, shunt controller, combination of series and combination of series shunt. Obviously, this classification has been done based on that FACTS controller interconnection with the transmission line. If that FACTS controller is connected in series with the line, then it is called as series controller. So likewise, shunt controller, if there are multiple transmission line having their individual series controller, so they need to control in a coordinated manner. So that can be called as combined series controller. Or if that two series controllers are having a common DC link to connect their DC sides together, then that series controller is called as IPFC, which stands for interline power flow controller. Similarly, series shunt controller is nothing but one series controller and one shunt controller is there, and their DC side are either they are controlled either in a coordinated manner or they are having a one common DC link to which through which they will do the exchange of real power, and that is called as UPFC, that is Unified Power Flow Controller. So that discussion we had already in the last lecture. In that we also discuss what basically the controller is. So that controller may be a simple static variable impedance like capacitor or reactor, or it may be a voltage source of fundamental frequency or subsynchronous frequency or the harmonic frequency or the combination of that. And basically in principle, it inject voltage in series with the line, and as long as that injected current is in quadrature with the line current, it exchange only the reactive power. If that injected voltage is not in exactly quadrature with the line current, then it can have both real as well as reactive power exchange with the transmission line. So similar to that, shunt controller is also can be a variable impedance or voltage source of fundamental subsynchronous or harmonic frequency or the combination of that. So in general, we can say that shunt controller inject current in the transmission line, and as long as that injected current is in quadrature with the line voltage, it exchange only the reactive power. And if any other phase relationship that injected current is having with the line voltage, then it can have both real as well as reactive power exchange capability. Now here the further detail, निंबा जरा हे लावून द्या, पडदा लावून द्या. अहो निंबा निंबा नाही का एक मिनिट. Now here we discuss the relative importance of these FACTS controllers. So whatever four controllers we seen, so how they are relatively important over each other for a particular objective function or particular we can say objective or task to perform in the given power system. So that we need to discuss. So first of all, if we talk about series controller, so basically what happened, this is the transmission line. And in series with the transmission line, we are using the series controller, that is series FACTS controller. So here as an example, if you see, this is the example of an series FACTS controller. Now, here what we are doing, we are injecting the voltage such that it is in quadrature with the line current, then it can exchange the reactive power with the transmission line. So because of that injected voltage, what happen? It will change the overall driving reactance of a total reactance of a line. We can say it is changing, that is, it is modifying the reactance of a line, or it is modifying the voltage drop across the transmission line, it is modifying. If it is modifying X, keeping EL constant, then it is changing the current flowing through the line, which is what EL divided by X. And as the current is changing, it is changing P. Because for P, we know the equation is what? E1 E2 by X into sine of delta.
Sir, you're not audible.
How the power flow through the transmission line can be controlled?
Hello, sir. Sir, you're not audible.
Hello, sir.
Oh, sorry. Now, am I audible?
Yes, sir.
Yeah. So in series controller, what we does, we inject the voltage in series with the line such that by mean of it, either we are modifying the impedance of a transmission line, series impedance of a line, or we are modifying the voltage drop across the transmission line, or we can say we regulate the current flowing through the line, or we can say we regulate the power flow through the transmission line. So series controller is the most effective way of controlling the current flowing through the line and the power flow through the line, as well as the to damp out the power oscillation. That power oscillation which may cause, because of always there is a variation in the load. So because of that, there is always small frequency oscillation of power flows through the line. So that can be damp out, or the power flow can be regulated, or current can be regulated by means of a static series compensator. As well as in earlier discussion, we also mentioned that this static series compensator rating is very small or fractional of that of our overall MVA rating of a transmission system. A small size of compensator is sufficient to regulate the more amount of power for the given transmission line if we go with a series controller. So that is, we can say, the significant control over the power flow can be achieved by means of a static series compensator. Whereas static shunt controller, if we talk about, then that static shunt controller is what does? It is injecting the current, and according to that current in phase relationship with the line voltage, in phase relationship with the line voltage E. Suppose this is E1 and it is at this end. So how this current is making phase with this E1 According to that, it exchanges the real and reactive power with the transmission line. And by exchanging that real and reactive power with the transmission system, it maintains the voltage at the point of connection of it always constant. Means the objective of shunt compensator is what? To maintain the voltage at its point of connection to the desired value. So if your objective is to maintain the desired bus voltage to particular bus voltage to the desired value, then you can go with a static shunt compensator like capacitor banks we are using in the substations to maintain our end bus voltage to the constant one with the variation in the load. But if your objective is to enhance the power flow through the transmission line or to damp out the power oscillation, then I think it is better to go with the static series compensator. Obviously, as static shunt compensator is maintaining the voltage at a particular point, it's not mean that static series compensator is not suitable for regulating the voltage across the transmission line. It is not so. Because even though for a series compensator, whatever voltage we are injecting, we are changing the voltage drop across the line. And as we are changing the voltage drop across the line, obviously this is controllable. So by means of that, this bus voltage is controllable. E2 is controllable. Or E1 is controllable by controlling that EL. But here, in order to control this E1 and E2 to a particular value, if we control the EL, that is going to control the flow of power through the transmission line also. Means the voltage at a particular bus we can maintain by regulating the power flow through the transmission line. And obviously there is not necessary that there is always a solution that for maintaining a voltage, how much power we have to pass through that line, but that power flow may not be as required by the load. So like that way it is possible. So in general, it has been concluded that if you want to regulate the power flow through the line, you go with a series compensator. Obviously, that is going to also affect the variation in the voltage of that buses also. But we can't maintain to that bus voltages to the desired value. If you want to maintain that bus voltage to the desired value, you have to go with a static shunt compensator. As usual, if your objective is to maintain the voltage of the bus to desire, to enhance the power, as well as to damp out the power oscillation. So these all objective function you want to get it done. Then rather than going series or shunt compensator separately, you can use a combined static series and shunt compensator. That is UPFC. You can use a static shunt and series compensator, that is UPFC. And using that UPFC, it is possible to maintain to control the flow of power, as well as to control the bus voltage, as well as to control the damp out of the power oscillations, and so on. So this is what the relative importance of this different types of FACTS controller. Now again, as in this particular controller, if your converters are provided with simple DC to AC converter having DC side a simple small DC capacitor, and the voltage across that DC capacitor we are transforming to AC side by controlling the switching of the converter. Now, in this case, maintaining this angle E in quadrature with the I is possible. But if E angle you are making something other than 90 degree with the I, then it is not possible because the capacitor which is there on DC side get discharged. Means real power exchange is not possible. Real power exchange is not possible with the DC side provided with the small capacitor. So in order to do the real as well as reactive power exchange is possible, no problem. But real power exchange if you want to do, then the DC side of the converter has to be provided with the storage. DC side of the converter has to be provided with the storage. And whenever there is a storage, it is possible for us that to deliver the real power from the storage to the transmission line, or to take the real power from the transmission line and store it to the storage. Means along with reactive power exchange with the transmission line, it is possible for us to exchange the real power as well. Now, in this case, it is possible for us to make the angle of injected voltage with the current to any value as you require to exchange the real and reactive power with the transmission system. But that is not possible here because there is no any source of real power on DC side or any storage for the real power on DC side. So that's why only reactive power exchange is possible with this combination, whereas both real and reactive. So similar is the case. Here it is shown series controller with the storage. Here it is shown shunt controller with the storage on DC side, or UPFC along with storage. UPFC along with storage. That is, we call it as a unified power flow controller. Now, about the use of power semiconductor devices, here if you see, this power semiconductor device is what? SCR. That is silicon controlled rectifier. And it is a we can say controlled power semiconductor device. By means of that, we only able to control the turn on of it. By means of that, we only able to control the turn on of this power semiconductor device. But the turning off of it, that is SCR, is either we need to use the line commutation or force commutation or any other external communication has to be utilized. Means what? This power semiconductor device is having turn on control, but turn off control is not there. Means it is not a self-commutating device. It is not a self-commutating device. Whereas if it is IGBT, like symbolically it might be shown somewhere here. Yeah. If it is IGBT, like your gate terminal is provided with the cross representation, that is, it is a self-commutating power semiconductor device like IGBT, insulated gate bipolar transistor. Means by means of this gate terminal, we were able to turn on as well as off the power semiconductor device. Turn on or off the power semiconductor device. That is what called as self-commutating power semiconductor devices. Now, by means of configuration of DC side of a converter, there is a classification of converter that is called as voltage source converter and current source converter. Voltage source converter and current source converter. Here, this is the figure for voltage source converter. This is the figure for voltage source converter, in which DC side of a converter is provided with a small DC capacitor, and the voltage across that small DC, call it as a VDC, is transformed to AC side of the converter as a VS, which is controlled by means of controlling the switching of your converter. In the coming lecture, I will dictate you one particular two-level converter and how that DC is transferred to AC side by controlling the switches. That we will discuss in detail actually. So this VS is equal to what? The switching function ES into the DC voltage. Basically, when we convert DC into AC means we are not doing anything rocket science there. We simply regulate the switches such that that is a power semiconductor switches I am talking, such that DC will look like positive half of AC and negative half of AC. So like that way switching has been controlled so that the alternating current square wave AC voltage waveform get generated on the AC side, and then the fundamental along with all other harmonic component of it is having, so that harmonic component can be filtered out with the use of filter, and the remaining AC is obviously kept up to the level of your transmission line voltage by mean of an coupling transformer. So here when the DC side is represented by a small DC capacitor, which is the equivalent of voltage source. Quotation in फाइल अलॉन्ग एक वेगळी फाइल बनवते सेपरेट मॅनेजमेंट. So when the DC side is represented by a DC capacitor, which is nothing but the source of voltage, so that's why it is called as voltage source converter. And here, as I said, by controlling these switches, this DC voltage we are reflecting on AC side, which will look like a AC. That's why it is called as AC voltage. Similar is the case for current source converter. In current source converter, the DC side of the converter is represented by a inductor, represented by the inductor, which is the source of current, That's why it is called as current source converter. And this DC side, that is IDC current of the inductor, we are transferring to AC side as a AC current by controlling this switching of the converter. And now when this AC side current is passed through the leakage reactance of coupling transformer, the voltage will be established, and then according to that transformation ratio of that coupling transformer, that voltage was get transferred to the level of your line voltage. So in that way, that current source converter will means here the DC link current is constant, and by controlling this current flow from DC side to AC side, we were able to control the reactive power exchange by this. Whereas VDC is constant in current voltage source converter, and by controlling this switching, we control the current exchange by this. Magar suppose we want to do the reversal of direction of power flow, means power flow from this side to this side, the direction of current is something. Let's say this is the direction of current for power flow from converter to line. But when power flow from line to converter, then the direction of current means by reversal of current direction, the power flow reversal has been done in voltage source converter. Whereas in current source converter, the reversal of power flow can be done by establishing the reverse voltage. By establishing the reverse voltage across the inductor, means the direction of current is same. Either we exchange, means absorb or inject the reactive power, the direction of current is same in current source converter. The direction of voltage is constant, voltage source converter. Now here there is a one example mentioned that voltage source converter it is, but it is having an storage. As I said, this simple voltage source converter or current source converter are capable only the reactive power exchange. Because if we control these switches such that this V is making an angle, or this V is making an angle such that whatever line current will be there, so it is rather than quadrature it is. Then in that case what happen? Real power exchange will be happen, and because of that this capacitor will get fully discharged within a cycle. So once it is get fully discharged, it won't charge and its working will stop. So in order to exchange the real power as well, we should have the source of power to the DC side, and that's why there is a storage. Obviously the interface, the purpose of interface is that if your storage is at some different voltage level, whereas your converter DC side capacitor is at different voltage level, so In order to match that voltage level of DC side capacitor and that of storage, you need to have some electronics interface like buck or converter or boost converter might be there and like that. So as I said, this converter as provided with the storage is able to exchange real as well as reactive power with the transmission line. So because of that, this converter will be more effective in case of damp out the power oscillation, in case of damping out the power oscillations. Now, this is what is the difference between voltage source converter and current source converter. Obviously, it is voltage source and current source converter that are based on power semiconductor devices which are self-commutating, power semiconductor devices. If we use SCR and if it is a current source converter, that is what you studied in high voltage DC transmission system. So that converters are current source converter, but they are with the we can say only controlled power semiconductor devices which don't have the self-commutating capability. Now, along with this, there are some other devices. So, as I said, these are the FACTS controller. So, there are some basic definitions uh, as per IEEE standards mentioned there in the book. So, we should be aware of that definition. Flexible electrical power transmission. Flexibility of electrical power transmission means what actually? Flexibility of electrical power transmission means what? The ability of electrical transmission system, the ability of electrical transmission system to accommodate changes in the operating condition while maintaining the steady state and transient stability limit constant, or there should be some steady state or transient stability margin. By keeping that margin, how we change the ability to modify or to accommodate the changes in the operation of the power system, and that changes may be like change in the power flow through the line, damp out the power oscillations. So if we want to operate that particular power system under some particular operating condition, so in view of that, how we can modify the parameters of that transmission line so that it will accommodate that changes. So the flexibility of electrical power transmission as per IEEE standard, the definition is what? The ability to accommodate changes in the electrical transmission system or operating conditions while maintaining sufficient steady state and transient margin. Similarly, FACTS का definition दिया है यहाँ पे flexible AC transmission system. That is nothing but whatever conventional alternating current transmission system is there, along with that some power electronics base or other static controllers are incorporated in order to enhance the controllability or increase in power flow capability of that transmission line. That is what the flexible AC transmission system. And when we talk about the FACTS controller, means flexible AC transmission system controller. So it can be a simple static or electronics based device which provide control of one or more of the parameters of the AC transmission line in order to achieve the objective like enhancing the power flow through the line or maintaining the voltage across that line to desired, like that. So for this, as we discussed, is voltage source converter based shunt compensator, that is also called as STATCOM. So only this is voltage source converter base and this is current source converter base. So it is called as STATCOM. So this is the STATCOM along with storage. Here are some example like damping resistor. First of all, we will see this is simple inductor, which is the sink of reactive power, means absorb the reactive power from the transmission line. By mean of mechanical switch, we can control it. Means by closing that switch, we connect the reactor to the transmission line. By opening of switch, we can open the reactor from the transmission line. Similarly, the another one that is mechanically switched capacitor, that is the source of reactive power. So by means of that, we can inject the reactive power into the transmission line. So it is simple called as inductor, capacitor as a source of reactive power. Filter, we know the filter is used to filter out some unwanted harmonic present in the line current or line voltage. So the filtering is done by means of resonance concept. Means for that harmonic frequency, we create the resonance between capacitor and the inductor, and because of that resonance, it offer a low impedance path for that harmonic current, and that's why rather than passing that harmonic current ahead, it will get bypass. It will be get grounded through this filter. But fortunately, this filter itself can be source or sink of the reactive power according to their value of capacitor and inductor. Because for fundamental frequency, that capacitor and inductor will offer some capacitive reactance and inductive reactance. And according to that, they can inject the reactive power into the transmission line or absorb the reactive power from the transmission line. Means their inductor will absorb and their capacitor will generate. And the mismatch of that is effectively, injecting the reactive power or absorbing the reactive power from the transmission line. Similarly, TSC, that is thyristor switch capacitor. So here this thyristor switch capacitor is simple capacitor bank, but rather than mechanical switches, it is having a thyristor as a switches. It is having a thyristors as a switches. So by controlling this turning on of thyristors, we connect this capacitor to the line or disconnect it of the line. So here thyristor power semiconductor devices are simply used as a switches. Then next one is thyristor switch reactor, means mechanical switch is replaced by the thyristor, that is called as thyristor switch reactor. But here in this case, if these thyristor switches are controlled by controlling their ignition delay angle, means rather than turning them on at alpha is equal to 0, if we go to delay it, so as we go to delay it, according to that, the voltage which has to be established across the inductor will be delayed accordingly. And according to that, the current flowing through that inductor will also get controlled. Means the magnitude of current flowing through that given inductor, we can vary from 0 to maximum possible value by means of controlling the ignition delay angle alpha of your thyristor. And as we are able to control the current flowing through this inductor, so it means that we are able to control the reactive power absorbed by this inductor from minimum 0 value to maximum whatever rated current into the inductive reactance offered by that inductor. So in this range, the reactive power absorbed by this thyristor controlled reactor can be utilized. Obviously, when these thyristors are switched for ignition delay angle alpha is equal to 0, for keeping it on, and alpha is equal to 90 for keeping it off, then it can be called as a thyristor switch reactor. Means this thyristor will simply use as a switch to turn it on, to turn it off. But if we keep the alpha in between of this 0 to 90 degree, then according to that, the current flowing through this inductor is get controlled, because for 90 degree the current was 0 because it is open circuit. But 89 if we talk or 88 we talk, very small current will flow through that inductor and very small amount of reactive power will be absorbed. So smooth control over the reactive power absorbed by the inductor, smooth control over the reactive power absorbed by the inductive reactor can be possible. So these are some specific FACTS controlling device, FACTS controller, which are used in the transmission system in order to regulate the parameter of that transmission line in order to achieve certain objectives. Here figure D is damping resistor. So here simple resistor is used to damp out the power oscillation. But it is connected to the transmission line. It is connected, rather than mechanical switches, it is connected through a power semiconductor switches. So by mean of this FACTS controller, we modify the parameters of the line. So related to this, there are many more definitions available in the literature. So some of that has been summarized here in this particular book. So as earlier I was told you about flexibility of electrical power transmission means what, then FACTS, that is flexible AC transmission system, means what, or FACTS controller means what. So similar to that, there are some specific definitions for some particular FACTS controller like STATCOM, SSSC, UPFC, IPFC. So that all definitions are available here in this particular book. So you please go through that and try to understand the what particular specific difference is there among uh, because you might be heard while searching for project topic, there were terms like static VR compensator, static VR generator, sometime it is synchronous condenser, static voltage regulator, sometimes STATCOM. So somehow these all are compensating, reactive power compensating devices. These all are. Some of them are shunt connected device, some of them are series connected device. But there is a slight difference in their operation or in their regulating parameter of a transmission line, and that is differentiating their title as specific to justify that particular difference or capability, or we can say identity, that particular device is having. Actually. So I think in the next lecture we will see that definitions along with how the voltage source converter or current source converter uh, operates, uh, and the concept behind converting DC to AC or AC to DC, and how we regulate that, control that from zero to maximum possible value. So that understanding point of view, we will discuss, have a discussion in the coming lecture. For today, actually, we will stop here. Actually, since morning, I have many more lectures. Again, I have to go for practical from this 2:30. So let me have some 10 minutes break. So that's why I would like to stop here only. We will see that remaining topic in the next lecture, because curriculum wise, if we see the basic types of FACTS controller, brief descriptions and definitions that we already started discussing. And lastly, the advantages of FACTS technology or benefits out of FACTS technology that we will discuss. And by that, we will conclude this module 1 actually. So, okay, you all please mark your attendance right now. Please mark your attendance. Those who mark can leave the meet, no problem. Those who mark the attendance can leave the meet.